Okay, so let's start this new event in the online summer series, summer seminar series on conceptual modeling. So today we are going to have a very important person, as any other person in this series, but today it's particularly important for me because it's the person I admire most in the area of conceptual modeling. This is Terry Halpin. And before going on with Terry Halpin, though, I would like to remind you that next week, our group, the KRDB group in Bolzano, is organizing another major online event with something like 12 conferences in parallel spanning for 2 weeks. It's called the Bolzano Summer of Knowledge. This was planned since many years to happen in September this year, and then, well, we had this pandemic, so this moved to be an online event. Many other conferences within this Bolzano Summer of Knowledge thing has been moved to next year, but still it's a quite big event. So I suggest you that you Google the Bolzano Summer of Knowledge and check that all the kind of events and important keynote speakers that will happen starting from next week. Okay, let me go back to Terry. As I was telling you, for me, Terry is the most important authority in conceptual modeling for relational databases, for information systems, both from the foundational point of view and actually the industry point of view. And you will see this from the kind of working life he had. So he started with a PhD. He has a basic education in philosophy. So as a philosopher, he did a PhD thesis on the logical foundation of information systems, where he actually introduces what is nowadays called ORM, the object role modeling notation, which at the time was, this was in 1989, was somehow already competing with the most popular modeling, conceptual modeling notation, which was ER. And then what he did after his philosophical studies and this logical foundation of information systems, he moved to industry and immediately acted as a main thinker behind and the main person behind one of the most interesting conceptual modeling tool that I can ever imagine. It was called InfoModelers. At the beginning of the 90s, he had his own company. Then this company was bought by Visio, and then Visio was bought by Microsoft. And when the company was bought by Microsoft, he became program manager in database modeling at Microsoft. I guess after a few years, maybe 10 years, if I remember well, he got pissed off by the fact that he was working for a major corporation and went back to research. Now, about these InfoModelers, this still is an amazing idea, which is still has to be finalized somehow, because, well, InfoModelers was a very powerful tool, and when this was bought by Microsoft, many times it happened when companies are bought by major companies, it has been depotentiated. It has been reduced to have fewer features than at the beginning. And in fact, Terry then is working with another company now in the States, which I think is Econs or something like this, called which now develops a plugin for Visual Studio, Microsoft Visual Studio, since basically Visual Studio was an evolution of his own tool anyway. So he went back to university, so was professor in Utah, principal scientist at Logic Blocks. Again, you see, you have this formal foundation, but also real application. Logic Blocks is a foremost company that has this idea of doing information system modeling and applications using well-founded ideas, like, well, in this case was data log stuff. Then recently he's back to teaching at Queensland University of Technology, and I guess if you really want to know more about his work, I guess there is a major book called Information Modeling and Relational Databases, which is the Bible for anybody willing to understand what kind of implication has doing conceptual modeling for information systems seriously. He also wrote a number of books which with a more applicative view and with exercise and stuff. So this is the talk I'm expecting most in this series. So Terry, welcome to EROSS.
Thanks very much, Enrico, for those very kind words. Okay, let's move on to the talk then. This is presentation on reference scheme modeling. It's about different ways you can refer to or identify objects of interest in the business domain. So I'll give a simple introduction to the basic ideas, then we'll look at simple reference schemes where you can refer to or identify an object using a single value. Then compound reference schemes where you need to use a combination of two or more. And disjunctive reference schemes where you use a disjunction of ways of referring. And then context-dependent reference schemes where your preferred way of referring to an object depends on the context that it's in within the domain of discourse. Okay, there's two natural ways of referring to objects. By the way, I use the term object simply to mean an individual thing. Like in logic, it's the same as an individual. So it doesn't have the connotation as the word object does have in some other methodologies. There's two natural ways you can refer to things. One is ostension, where you simply point at the object you're interested in. And the other way is to use the linguistic expression. And there's two basic ways of doing that. One way is to use a proper name like Barack Obama. So within the universe of discourse, that refers to only one individual. Or the other way is a definite description, like the 44th President of the USA. So it's actually quite easy to model both those kind of linguistic expressions in a modeling method. And first one would be a simple reference scheme, and the second one we would typically use a compound reference scheme. For computer systems, you'll see some systems like using OIDs or object identifiers, which can either be visible or hidden, but typically not very helpful in having people understand what you're talking about. So whether you use object IDs or not, you should still have a human-based way of referring to things. And so you need your modeling method really to support linguistic reference schemes. And there's major difference in the way that popular data modeling and ontological modeling language support these. So I'm going to review 6 different systems really. The first, object role modeling. By the way, that originally started off as NIAM when I did my PhD way back in '89. Eckhard Falkenberg originally developed what he called object role model, did his PhD on that years before. Then she and Nyssen added a different graphical notation for it, introduced a modeling method. Robert Mearsman introduced subtyping, and they had a grouply controlled data that actually developed. It was then called NIAM. Now, Eckhard and Shear came to the University of Queensland, where I was, and I picked it up, and I was teaching there. And it was years later when I modified and extended NIAM significantly and went to the States, and the company I was working for at that time wanted to change the name, so I said, oh, we'll just call it ORM. It's similar to what Eckhard originally called his. All right, so there's ORM, there's UML, Unified Modelling Language. There's Barker is my favourite version of entity relationship modelling. The one, pioneered by Richard Barker and others. Then there's relational database technology, the web ontology language OWL, and Logical is Datalog on steroids. I actually worked for a company that developed Logical. So understanding how the languages support the reference schemes is needed if you're going to model them at all, but also if you want to transform between them, it helps to understand. So let's move on to simple reference schemes. Now, some of you won't be familiar with the object role modeling notation, so let me briefly indicate. This is a fragment of an ORM meta model. The simple, there's two meta models in ORM. One assumes you're only talking about a single model, and that's what this one does. And in that meta model, an object type can be identified by a name. So like country is an object type. A type is a set of all possible instances. And within a single model, you can identify an object type simply by its name, like country, person, employee. Now, object types in ORM are displayed graphically using a soft rectangle. And if it's a solid line around it, it's an entity type. So I've got there an object type is either an entity type or a domain value type or a data type. So this is subtyping. The arrow is indicating that the lower type is a subtype of the upper type. The exclusive OR symbol here, well, basically it's an exclusive OR. So each object is either an entity, a domain value, or a data value. And there are some examples of entity types, some examples of domain value types like country code, family name. A domain value, an entity, by the way, gets identified either using a proper name or a definite description, and typically changes its state over time. Doesn't have to, but most entities do. Domain values are constant throughout time, and so are data values. The domain values are identified simply by their type name plus a literal. So the country code CH, first you say the type is country code and the literal is CH. Data type is just things you're familiar with. When you get down into a database, you're dealing with strings, unsigned integers, whatever. What we've got here is a relationship saying a domain value type maps to a data type. And the dot here indicates that it's mandatory. So each domain value type must map to a data type. And the little bar here indicates that if you pop, by the way, these little boxes here are called roles. A role is a part in a relationship, and you can populate a role with a column of instances. So this is saying if I populate this role with a column of instances, then these instances are unique. They're not allowed to be repeated. Over here, I don't have a uniqueness constraint, so I means I can repeat them. So you'll see string is there twice. Right, here's an example of the difference between a domain value and a data value. So if I take Switzerland, right, I can identify that using the country code CH. The actual data value is just a string CH, right? Now, the International Air Transport Association code, CH, what that does is identify actually the Bemidji Aviation Airline, which is based in Minnesota. But that code is also represented by this string. So the string CH doesn't have the additional semantics over here. Excuse me. Country code's not the same thing as an IAT code. They both get represented by the same string, but these have additional semantics. That's why we call them domain values, because they have semantics relating to the domain. So essentially, you've only got three kinds of objects. You've got entities, you've got domain values, and you've got data values. And in ORM, you're allowed any kind of object to play the subject in a fact reading. A fact is a proposition taken to be true by the business. So I could say the country CH is based on the name Latin. So Switzerland's got, 4 official languages, German, French, Italian, and Romansh. So to stop any bum fights, they said, let's choose Latin then, and nobody will object for having their code based on Latin, Confederatio Helvetica. The person title MR is restricted to the gender name male, so Mr. goes with male, of course, and furs are synonyms. And here I've got domain values as subjects in the sentences, right? And you can model that directly in relational databases and logical. But in UML, ERNL, you can't do it directly. So you have to cheat in those methods and artificially remodel domain values as entities. So here's an example of a simple ORM schema. I got each employee is identified by a number, is of exactly one gender. Gender is identified by codes like M and F. Each employee has exactly one person title. Now, some person titles are restricted to only one gender, like MR for males, MS for females. Things like DR for doctor, no, that's not restricted. So it's optional for a person title to be restricted. What we've got over here, you're probably familiar with the subset symbol. This is a subset constraint saying, look, if I take the employee gender code pair here from saying an employee has a person title that is restricted to the gender, then that pair has to also appear here. So the set of the employee gender pairs here is the subset of the set of employee gender pairs there. If you're using a tool like Norma, then everything is automatically verbalized. So if you touch that, that gets verbalized. So if some employee has a person title that's restricted to a gender, that employee is of that gender. So that's what it means. In UML, you might start off by saying, look, I got an employee class. I got employee numbers, the ID. I have person title and gender as attributes. So ORM doesn't use attributes. Every factor represented with relationships, right? Not attributes. Now, if you want to capture this constraint that I've got here, the subset constraint in UML, you'd want to say, well, I really want to say each person title is restricted to at most one gender. Then I can't do it if I leave it as an attribute. So artificially, I have to make a class out of person title, then use the text to represent the actual title, and then I'll have another attribute, restricted gender, indicating what I'm restricted to. And then to specify the subset constraint, now I have to add, I can't do it graphically, but I can add an invariant here. Here's my context person title. Here's my invariant restricted gen is either null, there isn't one, or it's the same as the gender of the employee. So you can do it in UML, but it's just not as natural. All right, referencing an entity by relating it to a single variable. That's the simplest kind of reference scheme you can get. So in this case, you can identify an entity by an individual constant or a single attribute or a single relationship to a value, depending on what system you're using. So each country could be identified by its country code or by its current name, like AU for Australia, CH for Switzerland. And if you had a country with a previous name, you could also say, well, the country that previously had the name Ceylon, that's Sri Lanka. right? Now, how do we model it here? In Norma, you say country is identified by code, but also has a current country name. This is a one-to-one association. And some countries, it's optional because I don't have the mandatory dot here, has, you know, a country optionally could have a previous country name, and a country name optionally could be previously the name of a country. This X here is an exclusion constraint indicating a country name can't be both a current name and a previous name. All right. By the way, this dot with the that we've got in the ORM diagram is simply an abbreviation for convenience, so your diagrams don't take up too much room. You can automatically expand it to the underlying form, which is, this is shorthand for this. A country has a country code. Country code is of a country, and it's mandatory one-to-one. And the double bar here indicates that the unique, it's not just a uniqueness constraint, but that's the preferred one for identifying a country. So here I've got you can also identify a country by its current country name. So I could use either the code or the country name, but this is telling me, look, I prefer to use the code as my primary way of identifying the country. And if you map this to a relational database, that becomes a primary key. So using the Norma tool, this is the display you get when you map it to a relational schema. Here's your country. PK, that's your primary code. U1, this is unique, and here's another unique. But these are bold, indicating they're mandatory, whereas this one's optional. You kind of nulls there. In biography, you would do it like this, and in UML you'd do it like that. Now, only ORM captures this exclusion constraint. Biography, you can't do it graphically at all. So basically, people at first see ORM and say, oh, it's too complicated, it's got too many symbols, but sometimes the world in modeling is fairly complex, and sometimes you want to actually model it precisely. So it's handy to be able to actually capture all these extra constraints, which will help you detect bad data being typed in. All right, let's move on to the web ontology language, L. It's got it's got no standard graphic notation, but it's got 5 textual notations. Of those, Manchester syntax is easily the easiest to read, so that's the one I'm going to use in these slides. You can have named individuals identified by International Resource Identifiers, or IRIs. They can be based on actual proper names or be surrogates. And you can also add human readable labels. So assuming that IRIs are provided, you can model this ORM model in OWL like this. This a data property maps an entity type to a value type, if you like, right? They're data properties. And character is functional, so each country has only one country code. That's capturing that uniqueness constraint. That one captures that one. And then how do I capture the mandatory roles? Well, I declare country to be a subclass of the things that have a minimum of one country code. So it's basically every country code's got to have a country. So that captures this guy. Similarly, that one captures that one. And then we use has key declarations to capture these other uniqueness constraints on this side. They have no notion of preferred uniqueness, but at least using has key, it picks up that one. But one of the problems with data properties in L, if you're mapping from an entity to a value, you can't declare the relationship to be inverse functional. It's a bit of a pain in the posterium. So the best you can do is declare these has key declarations, which to capture these ones, but there are kind of limitations on them. They're not quite the same as a key in a relational database either. All right, let's look at another kind of simple reference scheme where you reference an entity by relating it not to a single value, but to a single entity. So in OWL, these are called object properties because you're relating entities to entities. And those ones you can declare inverse functional. So you wouldn't use has key with them. In OWL, entities may be named individuals, so you identify them by an IRI, or they can be unnamed, represented by blank nodes, which you write as an underscore. So OWL allows you to support reference schemes that identify entities by relating them to other entities. So the next slide will show that. In the next slide, top politician, I mean the politician who's considered to be the head politician, either a president or prime minister, for example, of a country, but not both. So in ORM, you might, top politician heads the country. It's 1-to-1 and make that the preferred identifier. Each top politician was born in some country, but a country, of course, can have many top politicians born in them. So if you map to a relational database, you get this. And here's sample data from 2013. Julia Gillard was the Prime Minister of Australia, but she was actually born in Wales, so the country is the United Kingdom, which has the country code GB. At least the ISO code is GB, not UK. So the top politician of Australia was actually born in the United Kingdom, which is perfectly okay in many countries. You don't have to be born in a country to be the head of it. Although some countries like the US say, no, if you're not born in the US, well, stiff cheddar, you won't, you're not allowed to be president. All right, in UML, you can do it like this. And Bakriya, you can't do it at all. So although Bakriya, you can have relationships as components of a primary identifier, you can't use it for the whole identifier. In OWL, yeah, you can do that. I'm not going to go through the gory details here. You can read it for yourself. You can get a copy of the slides. But the difference here, because I'm now mapping from an entity type to an entity type, I'm allowed to capture the right-hand uniqueness constraint here by saying it's inverse functional, rather than trying to use this has key declaration. That's Julia Gillard, by the way. So what's this saying? The top politician of Australia was born in the United Kingdom. Now you can record that without knowing the name of the politician. All right. In OWL, if you just want to say, look, the top politician of Australia was born in the United Kingdom, you could say, look, I've got some individual unnamed, so the underscore here, I'll just call it P1, but the underscore says, no, I'm an unnamed individual. And then I'm not going to name the countries here either. I've got this facts about this individual. So this unknown individual, P1, heads some country, let's just call it C1, but it's still unnamed. And this unknown individual was born in some unknown country, C2, all right? And then, but then I can say, hey, look, talking about that individual country C1 here, it's actually got the country code AU, and talking about that individual there, the fact about it has got the country code GB. All individuals may be named with one or more IRIs or be unnamed. This is a way of modelling it in ORM. Here's an example. I got a class country, has country code. Again, because I'm going to a value rather than an entity, I've got to get the right-hand uniqueness with a has key. I can say the individual Myanmar, that's an IRI for it. fact about it is got the country code MM. But I could also say, hey, look, the individual Burma, fact about it has got the country code MM. And an OWL system will be able to infer from that the individual Burma is the same as the individual Myanmar. Right, so one of the nice things about OWL is it can make some basic inferences. Of course, you know, Burma was the previous name for Myanmar. Some people still call it Burma by mistake. All right. Now, this is something weird. If you've never used OWL before, it takes a getting a bit of used to, particularly this has key property. Here I got this country has key has country code. So a country code refers to only one country. So I'm saying Julie Gillard was born in this country C1, and this country C1 has a country code GB. And then after that, so she was born here in Wales. I say the UK, I can introduce that as an IRI and say, fact about it, it's got the country code GB. So will an OWL reason now infer that the individual Julie Gillard was born in the country of the UK? You'd think, well, look, Julie Gillard born in C1, C1's got country code GB, UK's got the country code GB, so it must be the same thing. So surely you'd think the answer is yes, but no, the answer is no. And that's that's because this has key applies only to named individuals, and you know this where is it? She could have been born in this other country of which is unnamed, and we can't conclude it's got to be this one. So it's kind of weird, but that's the way it works. Another thing you got to watch out, when most people do just relational database stuff, they tend to assume everything's closed world semantics. In other words, you know, if I don't tell you it's true, you know it's false. So if I give you a constraint in UML or Barker-ER or ORM and say each person was born in some country, that is a constraint. So if you attempt to update and saying, say, a person, you record a person without also recording their birth country, that update will be rejected because you've got a constraint that every person that you reference in the database, you have to know that they were born in the country they're born in. But OWL is open world semantics, so its declarations are not constraints, they're just propositions. That so here, I got person was born in country in ORM, right? So it's an object property going from entity to entity. So the OWL code declares each recorded person was born in exactly one country, but it doesn't require that the system knows which country that is, right? So you might say, well, isn't that saying that each person was born in only one country because it's functional? In fact, they must be born in some country. That should mean that each person was born in exactly one country. Well, yes, it is saying that. It's saying, yes, it's declaring as a proposition that each person was born in exactly one country. Yeah, but it's not saying that you have to know what country it was that the person was born in. So if you like, it's saying, look, it's declaring that in the real world or in the domain of discourse, each person was born in some country, but it's you can have incomplete knowledge. You can know that each person was born in some country without knowing what that country was. So so again, if you're used to closed world semantics everywhere and you're using OWL, you gotta start to realize how different it is if you adopt open world semantics. All right, logical is this data log on steroids. It was developed by Logic Blocks. Good performance for large databases, unlike some data logs, and really deep support for logical constraints and derivation rules, especially recursive rules and it's decidable as well. It adopts the closed world assumption. If I wanted to take that schema and code it in logical, I could say, well, I got a country that has some country code, and that implies that this thing is a string. And then this top politician P, this is just saying, hey, that's an entity type. The square bracket here is saying it's functional. So country headed by a politician can only be one country, and it's also typing it. So the country headed by the domain and range, domain is top politician, range is country, and so on. Well, you can read it yourself, but it captures the uniqueness. To say you had only one country, it says, look, if the country headed by P1 and C and the country headed by P2 is C, and then P1 equals P2. So it's going to capture a uniqueness constraint, and this is capturing the mandatory role constraints. If you're a top politician, then your country headed has to be something, and your birth country has to be something. So it's capturing those two. All right, let's move on to compound reference scheme. So you identify an entity using a combination of two or more attributes or relationships. In ORM and OWL and logical, it's always using relationships, but in UML and biography, you can also use attributes. So here's a simple example. I got a room, is in a building, the room has a room number, and that combination identifies the room. This is just a unary, ORM allows unary relationships, right? A room is windowed. Not all rooms have to be windowed, so that's not mandatory. The fact that a room can exist without being windowed, this is declaring room to be independent, by the way. So instances of room can exist independently of playing roles other than in its reference scheme. Here I've got a building identified by number, but as a secondary reference scheme, it can be identified by its X and Y coordinates in combination. So that's an example of a compound reference scheme there, which is the preferred one, the double bar, and this is a compound reference scheme, but it's not the preferred one. The preferred one is the simple one, the building number. If you map that to relational data, but again, this is using the Norma tool. If you enter that in the Norma tool, and just touch, so show me the relational thing. This is what appears. So here's a building. See, the primary key is building number, but you've got a compound secondary key here, the X and Y coordinate combination. All right. Barkery, you do it like this. Unfortunately, the composite uniqueness constraint on the X and Y coordinates is lost. There's just no way of doing it. In UML, you do it like this, but again, there's no graphical way of capturing the composite uniqueness constraint. That combination there refers to only one building. In OWL, the is windowed, all the predicates in OWL are just binaries, all right? So you can't have unaries. Like in ORM, you can have whatever you want, unary, binary, ternary, quaternary, whatever length you want. In OWL, you'd have a binary data property mapping room to a Boolean data type. The rest of it's done in a fairly similar way. If you want to do it in logical can do almost anything, actually. I won't bore you with the incredible details, but if you feel like it, you can wade through all this and convince yourself that this actually formally captures the same model as that. So Let's move on to disjunctive reference schemes, where you refer to things by using a disjunction. So let's take, first of all, explain joint semantics for external uniqueness constraints. These are internal uniqueness constraints, which apply just to a single predicate. This circled uniqueness bar is an external uniqueness constraint, which spans roles from two or more predicates. Excuse me. So this is at the meta level. I got a role norm can be identified just by a role ID. Each role is in a predicate, also has an ID. Some roles have role names, like here I've added to this role, I've actually given it a name. It's optional norm. This is a bit like, you might think like an attribute name in ER or UML, but in norm attribute, these role names are optional. You put them in if you want. They can help when you're mapping to a relational database. It's a nice way of getting the column name that you want. So role names are optional, but if you do put them in, then within the same predicate, names must be distinct. So within a predicate, if we've got role name, combine that with a predicate, that goes with only one role. Right? Here I populated it. I got 4 roles, R1 to R4. These ones are in predicate 1. No, R1, R2 in predicate 1, R3 and R4 in predicate 2. Here I've got predicate 2, and role R4 has actually got the name, which turns out to be name. So I could identify role R4 either using the role ID R4, or I could identify this by saying, look, it's the name, it's the role named name in predicate P2. So here we've got inner joint semantics. So if you're mapping this to a relational database, what do you get? You get a role, the primary key role ID, and then you have a predicate ID and role name. The BNF, right? The square brackets indicate role names are optional. With inner joint semantics, I'm doing an inner join here between there and there, right? So here's my population. If I take R4, well, if I come down here, you'll just join across these. Here's your population. But because these 3 roles, R1, R2, R3, don't get names, the role name for them is going to be null. But if you do have a name, the combination of the name and the predicate can refer to only one role. That's what this uniqueness constraint here means. All right. So there's your inner join. And we're saying with inner join semantics, the constraint applies only to the inner join, not the outer join. Now, OM allows you to have outer joins as well. So here's a course. Every course has, it's primarily identified by code, also has a title, has exactly one title. Some courses are offered by department, some of them aren't. And now I'm doing an outer join here. So like I got course C1, got the title mechanics. Course C2 has also got the title mechanics. C1's offered by the physics department, C2 is offered by the maths department. And that's allowed. Different departments can use the same title for their courses. But we want to say that courses offered by the same department have got to have distinct titles. And that's what this uniqueness constraint here is doing. But we're doing an outer join at this case. So we've got the added proviso that nulls are treated as actual values. So you do your outer join, which gives you this, and we treat null as an actual value. All right, so that's unique. This would violate it. If I introduce now a course C4 that also had the title mechanics, both courses C3 and C4 not offered by departments at all, maybe just offered by visiting lecturers, but they're different courses. And I say, no, I don't want to allow that, would be too confusing. So you got to use different names. This would violate this outer join uniqueness constraint. All right, let's move on to disjunctive reference schemes a bit more generally now. You can use them as preferred reference schemes. In this case, a double bar is used. So your course, maybe you don't have a course ID or a course number. You just say every course has a course title and it might be offered by a department, but what this is really saying is if I don't have a department, I'm identifying you by the course title, but if I do have a department, the combination of course title and department does it for me. All right. The weakest general pattern for disjunctive reference is essentially this. You can have any number of predicates here, R1 up to Rn. You've got to have an inclusive orbit over here, and at a minimum, you've got to have an outer join uniqueness over here. There's your inner join part. Given anything on the right-hand side, there's at most one on the left-hand side that where all these relationships hold. And here's your outer join part. Here's a simple example. The one we were talking about, really, given any course title and department, there's at most one course that has that title and is offered by that department. And given any course title, there's at most one course that has that title where there does not exist the department that offers it. Here's a very simple idea of a really weak disjunctive reference pattern. I want to identify non-origin points on a Cartesian plane. Here we got ABC. That's my primary identifier, it's just a label for it. All right, but I could also identify them by a combination of the x and non-zero x and non-zero y coordinates, which is what this is doing. So if you take the B, it's got 1 and 1. If you take A, I don't bother recording an x coordinate for that. I just record a y coordinate. And if I see the opposite. Here's a more, that model was just an artificial one I made up for simplicity. This one's actually a simplified version of a real example. One of my PhD students many years ago worked for the Department of Primary Industries in Australia, and he had to do a botanical classification scheme of every known plant. So the actual model, believe me, is very large and more complex than this. But this will give you the basic idea. We've got every plant kind is in a genus which gets identified by a name. So, and some plants are identified purely by their genus, like Agrostis. Some other ones are identified by combining their genus with their species name, like Acacia interior is a wattle, right? And some others, you actually need the infraspecies as well. An infraspecies itself has a composite scheme. So eucalyptus as a genus species, fibrosa, and the rank in infraname SSP nubula. So that's a simple little compound reference scheme. Here's a more complicated compound reference scheme. This is just a subset constraint. Look, if I have an infraspecies, then I go to have a species name and so on. Now we get to partial preferred reference schemes. Here I've got a uniqueness bar, and there's another bar over the top, but it's got dots instead of a solid bar. And this is indicating this can be used to reference just some instances of the relevant entity type. So in this example, a top politician could be the president or could be the prime minister. And the one we had before, it had to be only one of them. But here it could be either. You could have two top politicians. Like, here's an example. I've got Narendra Modi. He's the prime minister of India. But we've also got Ram Nath Kovind, who's the president of India. All right. So here, they're both, in this model, they're both top politicians, and one of them's the president, one of them's the prime minister. Of course, it's X or here. You've got to be exactly one of those two. And here, each country has at most one president, has at most one prime minister, and the country doesn't identify this thing. It's only identifies some of them. This one identifies just the presidents in here. This one identifies just the the prime ministers in there. That's why this is partial preferred reference. Here's another example of that. A famous person, some of them can get identified by a popular name like Confucius instead of Konghui or Confucius. Some others can be identified just by a family name, like if I said Einstein, you know who I'm talking about. And some other ones identified by combining the family name with the given name, like Marie Curie and Pierre Curie, and both. So that's just an example. These reference schemes occur all over the place, actually. I remember, God, about 30 years ago, 40 years ago, we just ran into industrial examples where we just had to deal with the damn things. And so that was, I think, when the first stage I introduced disjunctive reference into ORM. And around about the same time, Bernhard Tollon in Germany was he was introducing disjunctive reference into his own version of ER. Anyway, let's move on. Disjunctive reference schemes, you can map them from ORM to relational database schemas, but they're not supported in the graphical notation Barker ER or UML. Our hash-key property's got inner joint semantics, so you can do the inner joint semantic cases that we discussed before, but if you want to do outer joins, you can do it, but you've got to remodel first. So if I want to do this in OWL, I'd have to first subclass, I'd have to partition top politicians into presidents and prime ministers in order to do it. Once I remodel that as this, then I can do it in OWL. As I said, in logical, you can virtually do anything. Logical uses a semicolon for the inclusive OR operator, and that's how you do it in logical. And you can go through that if you're so interested. By the way, that double slash there, that means just a comment. Let's move on. Context-dependent reference schemes, they occur all over the place. Also useful if you want to merge schemas, if you want to, if you have a very large systems that some of the schemas overlap, and in one system you might identify something as one way, and then some other system you've got talking about the same thing, but you're identifying it in a different way, and then you want to somehow integrate those systems or at least have them combine the information, then that's one example of context-dependent reference. Here's a very simple example. Here I got a person globally, I got people are identified just by a person number. Now, this is an academic example. So a person, it can be a student, it can be an employee, could be something else, but I don't know. It's got to be one of those. So this is an inclusive or. Each person is either a student or an employee. I might have some things about persons up here that I want to record, what's your gender or something. Well, okay, I'll use person numbers for that. When I get down to student, and I've got student-specific information, like what degree are you seeking, that I'm going to use a student number, not the person number. With employee, I've got employee-specific information, like what department do you work for, I'm going to use an employee number for that. So these are different numbers from person numbers. Then I might have a student employee who's both a student and employee, and I'm not going to introduce yet another number for that. I'll just reuse one of these I've got. The solid arrow here indicates I'm inheriting my reference scheme from this super type. So for student employee, I've chosen to identify student employees by employee numbers rather than their student numbers. So when I record this student employee tutors for a period, I populate this, I'll be using student number, I'll be using employee numbers, not student numbers. All right. Mapping and context-dependent reference schemes from ORM to relational databases. There's in the references at the end, there's a book Tony Morgan I put out in 2008 that's discussed in agonising detail on those pages. Barker, ER and UML have no direct support for this notion at all. However, UML's implicit use of voids for class instances provide support for global identifiers at least. OWL lets you have multiple IRIs for the same entity, and if you use this OWL same as predicate to equate individuals, you can provide basic support, but not full support for context-dependent reference. Logical can model just about everything we've talked about, but doesn't yet fully support multiple inheritance. At least it didn't the last time I used it. All right, to conclude, I've been rushing through some of this stuff, but you've got the slides with all the details. All right, reference scheme support. If it's simple, primary reference scheme, yes, you can do it in ORM, yes, you can do it in relational databases. Mostly you can do it in Barker ER, yes, you can do it in UML, mostly you can do it in L, and yes, you can do it in logical. Simple secondary reference schemes, like, you know, primary might be a country code, secondary might be a country name. Yes, you can do it in ORM, yes, you can do it in relational databases. No, you can't do it in Barker, what a bummer. No, you can't do it in UML. Oh, yuck. Our mostly logical, yes. Compound primary, you know, like person identified by combining family name and given name. Yes, you can do it in ORM. Yes, you can do it in relational. Yes, you can do it in Barker. Yes, you can do it in UML. Mostly you can do it in L, and yes, you can do it in logical. Compound secondary. So you might identify employee primarily by the employee number, but you might secondarily identify them by family name, given name, plus some extra thing you might want to add, like a middle initial or something, until you get something that's distinct. So yes, you can do it in ORM, yes, you can do it in relational. No, you can't do it in Barker. No, you can't do it in UML, mostly in L, yes, in logical. Disjunctive reference, like that botanical classification system we saw, yes, you can do it in ORM, yes, you can do it in relational database. No, you can't do it in Barker, yeah. And indeed, just about any other version of ER. No, you can't do it in UML. Mostly you can do it in L, and yes, you can do it in logical. When I say here no, I mean you can't do it graphically, all right? All right, context dependent, yes in ORM, yes in RDB, no in Barker, partly in UML, partly in L, and partly in logical. So, future research plans. What have we got? We've got a couple of minutes actually. Extending the Norma tool, full support for new disjunctive reference cases, including automated verbalization, automated mapping between Norma and all the other ones. So some of that's already done. Actually, before we jump to the references, maybe I can, let me see. Let me just alt tab to a, here's a, oh, come on. I'm trying to get there. There we are. I've opened up the Norma tool. He's got a patient identified by patient number. Smokes. I've optionally put in a role-name patient. Has exactly one patient name. Patient is allergic to a drug. All right. So when you work with domain expert, I'll open up the verbalization browser. See that? Each patient has at most one patient name. That's a uniqueness constraint. If I grab the whole lot, including the mandatory role, the dot, I get each patient has exactly one. And the fact that I don't have a uniqueness constraint on this one, it says, hey, it's possible that more than one patient has the same patient name. So in all, when you're working with domain experts, they don't have to see the diagrams. You can just print out the complete verbalization of the model and understandable and controlled English, right? Or whatever language you're in. One of my PhD students some years ago built her own tool, actually. Came out verbalization automatically in Bahasa Melayu, which is basically the Malay language, and she also did it in Mandarin, which was a little more work, but she did it. That's a many-to-many, by the way. It's only the combination unique. So this is saying, hey, it's impossible. Some patient allergic to more than one drug and vice versa. And then if you want to have a look at the relational model, there it is. All right. I don't know how it's coming out on your little screens, but it's just all automatic. So the idea is that the conceptual level, you do it all up here. And then if you want to add something new, let's put in something new. Let's grab patient. So I was born in a country. How do I want to identify a country? Well, let's just identify it by a code, eh? That'll do. And there's my new fact type, but it's got a pink around it indicating, hey, I'm in an error state. Well, you click on that, it tells you the error, you know, tells you what you've done wrong. Anyway, you can fix it up. I want to say let's make it mandatory to know their birth country. And it's still an error because it needs a uniqueness constraint with a lethic modality. In ORM, you can have a lethic constraint, so they've got to apply, and you can also have dionic constraints, ones that ought to apply. So let's just make that unique. And now everything's okay. So if I map that to a relational thing, you'll find, hey, look, there's an extra table in the patient called country code. That's probably not the name you want, so you can give it a name like birth country. That's naming the role, right? And now if we have a look there, all right, it's well, okay, I need to, this is kind of lower level stuff, but if I come down here, I can actually, I think I've spent enough time, but you can tell it, birth country, take fixed length. Well, let's let's give it a length. Let's say you can have up to, was it country? How did I do code? All right, that's all I need is 2 then. Now it's char 2. All right. Anyway, you can roughly see what you basically just use the fact editor, type in what you want, have it drawn for you, add your constraints, have it automatically verbalized for you so you can check it with the client, and then just have it automatically generate your relational schema, and you can pick what do you want, SQL Server or Oracle or whatever. Okay. That gives you a basic idea. Anyway, I don't need that anymore. Don't need to save that. I just realised I'd whipped through some of that so fast that I had time to give you a quick demo of the Norma tool at the end. Norma tool, by the way, is free, but it's a plug-in to Visual Studio. So just use the community version of Visual Studio. That's also free, and then Norma's a free plug-in, so it doesn't cost you anything. Enrico's team at Bolzano, by the way, have done some really clever work extending the Norma tool with very advanced logical inferencing techniques to actually check. For example, you want to check, do all my constraints, do they contradict one another, or things like that, and it can automatically pick up some of the things that Norma by itself doesn't pick up. Norma picks up most logical errors, but some of them are so arcane that you need a more advanced approach, and Enrico's group have done some really nice work on that. Anyway, here's some selected references and website. These slides are based on a paper that I wrote. This is the paper here. Came out in that journal. Here's the main textbook on ORM that Tony Morgan and I put out 2008. Here's a couple of more recent ones I put out. Object Role Modeling Fundamentals. It also explains how to use the Norma tool pretty easily. By the way, my website also has oodles of stuff you can download if you want to play with things. There's a couple of books there. Business Rule Community. If you want to explore more on ontological modeling and logical modeling, like the OWL and logical stuff, there's a couple of series I did for the Business Rules Journal that go on almost ad nauseam on that. ORM.net is my website. The ORM Foundation is Ken Evans runs that one. It's set up to a whole bunch of stuff. ORM Solutions, Matt Kurland runs that one. He's the main, well, he's basically the only coder for the Norma tool. But on that one, you can download some other stuff as well. There's a fact-based modeling group. ORM is an example of fact-based modeling, where you say, just give me the facts. Don't try to bias me towards saying some are more important than others. So I want to model this as an attribute rather than a relationship. Just treat them all as relationships, and it just depends on. That's an implementation decision whether you want to talk about attributes. So that's a lower level thing. So that's fact-based modeling, and there are a number of approaches, not just ORM. There's CogNIAM, which is like Schernison's current version of extended NIAM. There's a bunch of them around, and there's a whole group that have come up with a fact-based meta model. UML, that's the latest spec if you want it, and OWL, that's the latest stuff on it. So if you want to explore some of these further and you're not familiar with them, there's some brief references for you.